Systems of nonlinear equations. Let's do a little review. Solving a system of equations which has this form is finding where f of x and g of x intersect graphically. So we're finding a point of intersection. But we will solve our nonlinear systems of equations using the substitution method or the elimination method. So instead of spending the time graphing the two different equations, we're going to solve using substitution or elimination. These should be familiar methods from our days of solving systems of linear equations. So as a quick example of a system of linear equations that we should be familiar with, it might look something like solve 2x plus y equals 6 and 3x minus 2y equals 4. So here notice that x and y are to the first power, x and y are to the first power, so we have two lines. So we're ultimately finding where do these two lines intersect, if in fact they do. That would be our solution to a system of linear equations, but we solve it using either substitution or elimination, which we will review. Here's an example of what we're going to be solving in this section, a system of nonlinear equations. So something like y equals x squared minus 9, which is not a line, it is a parabola. And then 3x plus y equals 4. So as long as one of them is nonlinear, we have a nonlinear system of equations. Let's jump into our first example. We want to solve by substitution x squared equals y minus 1 and 4x minus y equals negative 1. And so here we're being instructed to solve by the substitution method. So what we want to do is solve one of the two equations for an individual variable and then substitute that into the other equation. For this example, I'm going to choose to solve the bottom equation, so the linear equation, 4x minus y equals negative 1, for the variable y. I'm going to choose to try to get y by itself. So I'm going to go ahead and do this work off to the side where I recognize that solving for y is adding the 1 to the left side and adding the y to the right hand side. So we get 4x plus 1 is equal to y. And now that I have y isolated, so a individual variable isolated on one side, I can go ahead and substitute that into the y variable for the other equation. So I'm going to go ahead and now make my substitution into the top equation, which is the quadratic, since we have x squared there. So our new quadratic is going to be x squared equals 4x plus 1 minus 1. So now my job is to solve this new equation, which should only have one variable in it. After I have applied my substitution, there should only be one variable involved in the equation, and there is. There's just x. So here we're going to go ahead and cancel the plus 1 and the minus 1. So we're really just solving x squared is equal to 4x. And then let's remember that we cannot divide by a variable or we may lose solutions. So here to solve this quadratic equation, I'm going to subtract the 4x to the other side. So x squared minus 4x is equal to 0 so that I can factor. So we can factor out an x and we're left with x times the quantity x minus 4 equals 0. And so we're left with the solutions to this equation being x equals 0 and x equals 4. Alright, so now what do we do with these two solutions? What are we really doing is we're finding points of intersection. So where does this line intersect with this parabola? So it turns out it looks like so far it's going to happen at two different locations, but I want the complete coordinate point. So I have the x value of one coordinate point and the x value of a second coordinate point. To find the corresponding y value, I'm going to go back to my equation that is solved for y. Y is equal to 4x plus 1. So if y is equal to 4x plus 1, then when x is equal to 0, y is equal to 4 times 0 plus 1. So y is equal to 1. So I have my coordinate point now, right? My point of intersection, one of them, is 0, 1. So I'm going to put 0, 1. I'm going to express my answer as a coordinate point. And then when x equals 4, we're going to plug 4 into y equals 4x plus 1. So we have y equals 4 times 4 plus 1. So we get out 17. So we have 2 points of intersection. We have 0, 1. And then my second coordinate point is 4, 17. Now notice these are coordinate points, so not intervals, so I'm separating them by a comma here. And since I was solving, right, anytime I solve, I want to put my answer in the braces. So I have these two solutions, 0, 1 and 4, 17, these two coordinate points where this parabola intersects this line. In general, we're not going to have the corresponding graph for each equation, but just to really confirm our answers, let's go ahead and take a look at the graphs of each of these equations on the same xy plane. So here are my graphs. So we have my parabola here, so that you can see that's y equals x squared plus 1. If I add the 1 to the other side, shifts my parabola up. And then here I have my linear equation, so that was y equals 4x plus 1. So we can see from the graphs that they intersect in two different places, and the coordinate points they intersect at are 0, 1 and 4, 17. So obviously if we had the graphs, we would carefully observe and make sure that we can see the points that they intersect, and that would be the answer. But if we aren't provided the graphs and we haven't, very detailed sketched them out, then we would use our algebraic methods of substitution or elimination. So we just practice substitution. Let's go ahead and try another example. This time we're going to solve by elimination. And the equations are 4x squared plus y squared equals 13. And x squared plus y squared is equal to 10. And I have this note on the bottom that says elimination is a good strategy when both equations have variables added or subtracted with the same exponents. So here I have x squared and x squared in each equation, and I have y squared and y squared in each equation. So to use the elimination method, what we can do is take any equation and multiply both sides by a coefficient so that when we add the two equations together, one of the terms will cancel. One of the variable terms will cancel. So what I'm going to go ahead and do is multiply the bottom equation by a -1. So whatever I do to one side of the equation, I'm going to do to the other, which is multiply by -1. So how I'm going to show my work here is I'm going to go ahead and put on top of this multiply by -1 to remind myself what I'm doing. So my bottom equation would become -x squared minus y squared is equal to -10. But I'm going to leave my top equation the same for this example. So I'm going to leave it as 4x squared plus y squared is equal to 13. And now I'm going to go ahead and add the two equations together, and I'm going to eliminate a variable completely. The variable I'm going to eliminate is the y variable, y squared, because I have positive and negative of the exact same term. So when I add these together, I'm going to end up with 3x squared. The y's cancel, as we said, is equal to 3. So I have 3x squared is equal to 3. And here I can divide both sides by 3. I'm just dividing by a number. So I have x squared is equal to 1. And this can be solved by taking the square root of each side, but of course plus or minus is going to come out. So I'm going to get x equals plus or minus 1. Alright, so this is not the answer. Remember, our answer to solving a system of equations is a coordinate point or coordinate points. So these are the x values of my coordinate points, and now I need to find the corresponding y values. Well, this time I don't have an equation that is already solved for y. So I can choose either equation here to solve for the corresponding y when I plug in these particular x values. So I'm going to go ahead and choose the bottom equation just because it has coefficients of 1 involved, so it feels like it's going to be a little bit easier. So I'm going to go ahead and say when x equals 1, So we'll do each one at a time. I'm going to plug 1 into the x value on the bottom equation here. So I'm going to say 1 squared plus y squared is equal to 10. So y squared is equal to 9. So if I subtract the 1 to the other side, so y is equal to plus or minus 3. So what happened was, with this x value, x equals 1, I have 2 different y values. So I actually have 2 coordinate points that are going to come out of this. I have 1, 3, and I have 1, negative 3 that are going to come from the x value 1. And then we have to do the same thing for x equals negative 1. So if x is equal to negative 1, then I'm going to have negative 1 squared plus y squared is equal to 10. So again, I'm choosing to plug it into the bottom equation, but I could do either one, any equation involving x or y. And so here, negative 1 squared is 1, positive 1. So if I subtract from the other side, I get the same thing as last time. I get y squared equals 9, or y equals plus or minus 3. So with negative 1, I also have 2 different y values. So I have 2 more coordinate points that come out of this. I get negative 1, positive 3, negative 1, negative 3. So these are my solutions. I have 4 points of intersection between these 2 different equations. So now, for the second time, let's go ahead and just take a look at the graph and confirm our answer. So we would not generally have the graph, but here we're going to go ahead and take a look at the graph and just confirm the answers that we got, our solutions. Well, here are our 2 graphs. So we have x squared plus y squared equals 10 is a circle, right, is a circle. So it has that form x minus h squared plus y minus k squared equals r squared. So we have a circle, and then here it's not quite a circle because of the 4 that's in front. It is, of course, an ellipse, an elliptical shape, so almost like an oval here. And so we can see that these 2 intersect in 4 different places, right? I have 4 different coordinate points. 1, 3, 1, negative 3, negative 1, 3, negative 1, negative 3, which confirms. Let's try another example. Let's solve this one by substitution. We have x times y equals negative 12, and then x minus 2y plus 14 equals 0. So here we want to solve by substitution, as the instructions say. And again, we want to go ahead and isolate, get one variable in one of the 2 equations by itself, right? So we want like x equals or y equals. Now on the top equation, it wouldn't be hard to get x or y by itself because we could simply just divide the other variable to the other side. But if we just start to think long term about that, now we're creating some rational expressions, right? So now we're going to create a quotient if we start to divide by x or divide by y. And oftentimes we don't want to deal with like fractions, so I would say the best thing to do is work with the second equation here and get x by itself, because that just means adding 2y and subtracting 14 to the other side. So here I'm going to go ahead and say x is equal to positive 2y minus 14. So again, adding the 2y, subtracting the 14 to the other side. And now I'm going to substitute that into the other equation's x. So I'm going to replace that x with 2y minus 14. So my equation will now be 2y minus 14, making sure to keep that in parentheses, times y is equal to negative 12. After I've performed my substitution, I should have an equation left with only one variable involved. Now here, let's remember, we cannot set factors equal to anything other than 0. So a common mistake would be to set, each factor equal to negative 12. I can't do that. I, in fact, have to distribute the y into each term. So I get 2y squared minus 14y. And then I'd have to add the 12 to the other side to get it equal to 0. And then I want to go ahead and solve this quadratic equation. Well, everything here is divisible by 2, so we can go ahead and divide both sides of this equation by 2 and end up with just y squared minus 7y plus 6 is equal to 0. Right, so just divide the 2 out, give ourselves a leading coefficient of 1, Now this is easier to factor. So it factors to y minus 6, y minus 1 is equal to 0. Right? If we distribute this out, we get this quadratic. And so my two solutions here are y equals positive 6 and y equals positive 1. But again, these are the solutions to this quadratic equation, not the solutions to the system of equations. I want coordinate points for that. So I'm going to go ahead and substitute each of these y values into any of the equations involving x and y. So I can plug these into the original 2, but the easiest thing, because I solve by substitution, is to plug into x equals 2y minus 14. It's already solved for x. So let's go ahead and do that, right? So we're going to plug it into x equals 2y minus 14. We'll plug in y equals 1. So x is equal to 2 times 1 minus 14. So we get a negative 12 out of there for x. So let's express that as a coordinate point. So as a coordinate point, it has to go x comma y, right? So it's got to be negative 12, 1. And then we plug in y equals 6 and get x equals 2 times 6 minus 14. So that's 12 minus 14, or negative 2. So remember, this is an x value here that has to go first. So negative 2, 6 is my second coordinate point. So these are my solutions to my system of equations. So this system of equations was a rational expression. So here we can kind of see, I'll pull this work to the side for a second, that this top equation is y equals negative 12 over x. And then if we were to solve the bottom equation for y to get it to be y equals, we would see that it's a linear function that looks like 1/2 x plus 7. So we have a rational expression, right, like a transformation of 1 over x. So it's going to be reflected over the x-axis with like a vertical stretch by 12. So we have a transformation of 1 over x, and then we have a linear function here. And we can see that they're going to intersect at two different coordinate points. So if I did just the roughest sketch, and we don't have to, I'm just kind of doing it to confirm my answers, here's what it would look like. So my transformation of 1 over x here, the reflection and everything, would give me a graph that maybe looks something like this. Right? And then 1/2 x plus 7 is going to give me a linear function. I'm being very just vague about it. But this is what's happening, right? I have a positive slope, positive y-intercept, and we can see that there are 2 points of intersection there, and we found those 2 points to be negative 12, 1, and then negative 2, 6. So those are the 2 points of intersection that we found. We didn't have to do it graphically. I'm just showing the graph to sort of confirm our answers. In the next example, we're going to solve by elimination again. We have 4x squared minus y squared equals 4, and 4x squared plus y squared equals 4. Now this is set up perfectly for elimination. We do have the same variables to the same exponents in both equations, but also we have these two terms that are already opposites of one another. We have negative y squared and positive y squared. So we don't even have to multiply an equation or maybe both equations by a coefficient on each side to sort of clear a particular variable. We can just go ahead and add these two equations together automatically. So we can go ahead and add down here, and we'd get 8x squared is equal to 8. So the y squareds are going to cancel. And that's going to leave me with x squared is equal to 1 if I divide the 8 out on both sides. And so x is equal to plus or minus 1. So now, again, our job is to plug in x equals 1 and x equals negative 1 into any equation involving x and y. And they both kind of maybe look equally as difficult to plug 1 and negative 1 into. So it doesn't matter which one we choose. I'll go ahead and just choose the top one. So if I let x equal positive 1, I get 4 times 1 squared minus y squared is equal to 4. So here, 4 times 1 squared, that's just 4. And if I subtract it to the other side, I have negative y squared is equal to 0. Or y squared is equal to 0. Well, that means y is simply 0. The only number you can square and get out 0 is 0. So there's no point in putting plus or minus, right? It's just 0. So the coordinate point that comes from this is 1, 0. That's one of my solutions. And then I'm going to do the same thing for x equals negative 1. And you can already maybe see what's going to happen because we're squaring it, but we're going to get the same thing. If I plug in x equals negative 1, 4 times negative 1 squared minus y squared equals 4 will again give us negative y squared equals 0. So y is equal to 0. And so my second coordinate point is negative 1, 0. So these are my two solutions. Now, a system of equations can have one solution, two solutions, three solutions, four solutions. It can have no solutions. So there's not a particular amount that we are in search of. We just want to make sure that we are accurately doing whatever method we're using, elimination or substitution, and following through to get all of our possible answers. In this example, we have no specific way to solve it, so we can choose the method that we want to solve this particular system of equations. And here what we have is 6e to the x minus e to the y equals 1, and 3e to the x plus e to the y equals 8. So definitely not linear equations, right? We're combining these exponentials together. And I would say definitely the easiest method to use here would be elimination. Because remember, substitution would require us to get an individual variable by itself, get either x or y by itself. And we can see trying to do that would definitely be a lot of work. But the elimination method, which involves adding the two equations together to cancel a variable, it's already set up for that. I can get rid of the y variable if I add these two equations together because I have opposites. I have negative e to the y plus e to the y. So I can start by just adding these two together and get 9 e to the x plus 0, the y stuff will cancel, is equal to 9. Divide both sides by 9, so I have e to the x is equal to 1. Now here, a lot of people will just see that the answer for x is 0, because e to the 0, anything to the 0 equals 1. And so you can just go straight to x equals 0, or if you want to, we can show how if we take the natural log of both sides, natural log of e to the x equals natural log of 1, because natural log and e are inverses, they cancel, and we get x equals ln 1, which we'd have to know, of course, natural log of 1 is 0. So we have one x value, and we need to find the corresponding y value to write out our coordinate point. Well, we can plug x equals 0 into either equation, and again, I would say either one is equally as difficult to plug x equals 0 into. So we'll go ahead and plug it into the top equation. So if I let x equal 0, I'll have 6 e to the 0 minus e to the y is equal to 1. Well, as we said, anything to the 0 is 1, so I have 6 minus e to the y is equal to 1. I'll subtract the 6 to the other side. Negative e to the y is equal to negative 5. Now here, we want to make sure and divide the negative out of both sides. Sometimes people want to take the natural log right away. I can't do that unless the negative is out of there. So I have to divide out the negative on both sides. I have e to the y is equal to 5. So how do I get that y out of the exponent? I have to take the natural log of both sides, ln e to the y, ln 5. And then again, natural log and e are inverses, so I get y equals natural log of 5, which can't be evaluated without a calculator, so we're just going to leave the answer exact here. And so we have one point of intersection when x equals 0 and y equals ln 5. So we have 0 natural log of 5 as our one and only solution, now one coordinate point, that solves this system of equations. So notice that we're bringing back previous topics, right? The ability to solve exponential equations. In this example, let's go ahead and try a system of equations involving trigonometric functions. We want to solve sine x plus y is equal to 0 and y is equal to sine 2x, but we only want the solutions. We only want the points of intersection between the interval 0 and 2 pi. So on this example, it's definitely set up for us to do the substitution method because I already have one of the two equations solved for a particular variable. I have y is equal to sine 2x. So I can simply plug sine 2x into the y of the other equation automatically. So we'll start by trying to solve sine x plus sine 2x is equal to 0. So again, I substituted 2x into the y because y is equal to sine 2x. So I have an equation that only involves one variable. And now we have to make sure to remember how to solve a trigonometric equation like this. Well, we're going to have to use the double angle identity for sine here. So we can't factor out a sine right now. I have to recognize the double angle identity that is involved. So I have sine x plus 2 sine x cosine x is equal to 0. So from here to here, the double angle identity for sine that we should know. And then we can factor out now a sine x, there's one in each term, to create a product. So if I factor out a sine x, I have 1 plus 2 cosine x is equal to 0. And now that I have a product, I can set each part equal to 0. So I can set sine x equal to 0. I can set 1 plus 2 cosine x equal to 0. So here, where does sine x equal 0? On 0 to 2 pi, remember. So sine x is equal to 0 at x equals 0. And also, x equals pi. So at the angle pi, the y value is 0. So we have two solutions here. For this equation, I want to solve for cosine x. So cosine x is negative 1/2 after I subtract the 1 and divide by 2. And so here, where is cosine negative? That's quadrants 2 and 3. And so we're going to have two solutions. And the reference angle is pi over 3. So we're going to have 2 pi over 3 from quadrant 2 and 4 pi over 3 from quadrant 3 as my two solutions. So within this one system of equations, I have to solve a trigonometric equation. I got 4 different answers, and now I have to plug those 4 answers into one of the equations involving x and y, but the bottom one is definitely the easiest, right? Because it's already solved for y. Y equals sine 2x. So we'll go ahead and put y equals sine 2x. And we're going to have to plug in each of the x values that we found from this part over here. So if I plug in x equals 0, so I would get y equals sine of 0, which is just 0. So we have one coordinate point. I'm going to start to list them down here. 0, 0 is one point of intersection. If I plug in x equals pi, I'll get y equals sine of 2 times pi. So again, we're plugging pi into this x right here. Right? So sine of 2 times pi, which is sine of 0, which is 0 again. So we have the coordinate point pi 0. And then we'll plug in x equals 2/3, or 2/3 pi, excuse me. So that's y equals, all right, let's see what's going to happen. If I plug in 2/3 pi into this x, we're going to get 4 pi over 3. So we have sine of 4 pi over 3. And that's going to be in quadrant 3, and sine is negative in quadrant 3. So we're going to have negative radical 3 over 2, because sine of pi over 3 is rad 3 over 2, but in quadrant 3, sine is negative. So negative rad 3 over 2. So we get 2 pi over 3. negative radical 3 over 2 as a third point of intersection. And then finally, x equals 4 pi over 3. Well, that's going to give us y equals sine of 8 pi over 3. If I plug in 4 pi over 3 into this x, the 2 and the 4 multiply, we get 8 pi over 3. And this is going to be in quadrant 2. So 8 pi over 3, this is 2 2/3 pi, right? So it's like going around the unit circle once, and then another 2/3 of the way gets us to quadrant 2. And in quadrant 2, sine is positive. So we already know it's going to be either positive or negative radical 3 over 2, because that's the reference angle, right? Pi over 3, sine of pi over 3, we should know is rad 3 over 2. So it's just a matter of finding out if it's positive or negative, depending on where this angle is. And 8 pi over 3 is in quadrant 2, right, where sine is positive. So we get positive rad 3 over 2. That corresponds to 4 pi over 3. So our fourth answer is 4 pi over 3, comma, positive radical 3 over 2. So these are my 4 different answers, right? And so here, I mean, it was set up for us in a way where y is already solved for to be able to plug these angles into. But remember, you could plug it into the other equation here, right? And so that would be like y equals negative sine x. So it doesn't matter which one you plug it into, you should still get the same